Hello class, in this lecture let's discuss relative equilibrium of liquids. So here in this topic, we will understand the behavior of fluids that is inside a container, and when the container is moving, either rotational or it is in rectilinear motion, what will be the behavior of the fluid inside that container. So let's start. For rectilinear translation, let's say we have here a moving vessel having a constant acceleration. So the tendency of the fluid inside this vessel is that the liquid surface or the liquid surface inside that container will tilt at a certain degree. So our liquid surface will have an angle of tilt from the horizontal. So we mark that as theta. So the forces present inside this vessel are the weight of the fluid, which is going downward, the normal force acted by the fluid. So since we have a motion which is going to the right due to the constant acceleration, so we will also have a reverse effective force. So whenever a body that is moving, so there is always an equivalent reverse effective force for that body. So when we form a force triangle using the weights or the forces present here in this moving body, we can now form a force triangle with an angle theta. So the angle theta is just the same as the angle of tilt of the liquid surface when it moves. So take note class, in this figure, this moving vessel is moving on a flat surface, okay? So there's no angle of inclination on the surface where the vessel is moving. So based on the force triangle, we have tan theta, we have the reverse effective force, the weight, the normal force. So as we recall, the solution in determining the reverse effective force, that is just equals to the weight of the body to be divided by acceleration due to gravity multiplied by the acceleration. Okay, so weight, we can have that. The normal force, that's still unknown. But since the easiest values that can be determined here are the reverse effective force, and of course we also have a given weight of the body. So we will just use the reverse effective force and the weight of the body in determining the angle of tilt of the liquid surface. So applying the tangent function, so tangent theta is equals to the reverse effective force divided by the weight. So when we substitute W over G on the reverse effective force to be divided by W, we will come up to the value of tan theta is equals to A over G, because the weight will be cancelled out. So what remains is A over G, or the acceleration of the body divided by the acceleration due to gravity. So that's how we determine the value for theta. So just take the arctangent of A over G, we'll be able to determine theta here. Okay. So how about the moving vessel is in inclined motion. So of course our acceleration is parallel to the plane surface where the vessel is moving. So first, determine the equivalent components, horizontal and vertical components of that acceleration, AV to AH. Then We can solve theta by applying this solution. So tan theta equals to AH over G plus or minus AV. So the sign for plus or minus will depend on the direction of the motion of the vessel. So if it is going upward, we use positive sign, and if it is going downward, we use minus sign. So we use this solution. Okay. For moving vessel in vertical motion, we use this solution. Okay. Gamma H in determining the pressure at the bottom, that's gamma H multiplied by 1 plus or minus A over G. So for vertical motion, the liquid surface doesn't change in its position. Okay, it remains horizontal. So positive for upward motion, negative for downward motion. Okay, so we're done with rectilinear motions of moving vessel. So let's now solve some problems. Sample number 1, we have an open tank which has a dimension of 1.7 by 1.7 and 1.3 meters deep. Contains water at the depth of 0.9 meters, and the weight of the tank is 3,500 newtons. So we have weight of the tank 3,500 newtons. The tank is acted by an unbalanced force of 12,000 newtons parallel to a pair of sides. Let's say this going to the right. So a force of 12,000 newtons is applied. Determine the acceleration of the tank. Determine the maximum pressure of the bottom of the tank, and determine the force acting on the side with greatest depth. Okay, so let's start for letter A. For letter A first, let's determine the acceleration. So as we recall, in physics, the force is equals to mass times acceleration. So let's determine first the total mass of this body. We have the tank as well as the water. So for the mass, let's just add the mass of the tank. Okay, so since we have a unit of Newton, it is in weight. So we divide it by G in order for it to be converted into mass in kilograms. So 3,500 newtons should be divided by, okay, let me write first. The weight of the tank, or the mass of the tank, is added by the mass of water. Okay. So again, the weight of the tank should be divided by acceleration due to gravity to convert it into mass. Then mass of water, we can use mass density of water multiplied by the volume of the water. Next, we substitute the given. We have 3,500 newtons to be divided by 9.81 meter per second squared, plus mass density of water is 1,000 kilograms per cubic meter. So the volume of water is the dimension, depth of water 0.9 multiplied by the width, the base width, which is 1.7, and the thickness, we have 1.7 also. This is 1.7. Okay. So also multiplied by 1.7 meters. Next, the mass is equals to, we can directly solve this, 3,500 newtons, 9.81 divided by 9.81 plus 1,000 multiplied by 0.9, 1.7, 1.7. Okay, centimeters. So the answer is 2957.778. That's in kilograms. Okay, 2957.779 kilograms. Now we substitute force equals to mass times acceleration. So the applied force here is 12,000 newtons. Okay, so we can substitute that here in force, and we also have the mass. So to find the A, we divide both sides by the mass, or simply acceleration is just force over mass. So the force is 12,000 newtons to be divided by the mass, which is 2957.779 in kilograms. So as we recall, Newton is kilogram meter per second squared. So kilogram will be cancelled out. What remains is meter per second squared, which is a unit of acceleration. So we divide the two. 12,000 divided by 2957.779. We have 4.057 meter per second squared acceleration. That's the answer for letter A. Letter B, determine the maximum pressure at the bottom of the tank. Okay, for letter B. So when the vessel moves, so let's draw the figure, and the liquid surface will tilt. So here's the figure of the new liquid surface when the vessel is moving at a constant acceleration of 4.057 meter per second squared. So we have theta here. Okay, so what's required here is to determine the maximum pressure at the bottom of the tank. So when the liquid surface changes in position, you can see here that the left side, the leftmost corner of this tank, is the one that has the highest pressure, because the depth of the fluid at this point is higher compared to the right side. Okay, so we will focus here on this point, let's say point A, as the point where we have the highest value of hydrostatic pressure. So first, let's determine theta in order for us to compute this total depth here, depth of fluid, let's say depth Z. So let's compute first theta. Theta is computed by the formula tan theta is equals to A over G. So we can now compute the angle by solving arctangent of acceleration divided by acceleration due to gravity. So arctangent of 4.057 meter per second squared divided by 9.81 meter per second squared. So the theta is equals to arctangent of 4.057 divided by 9.81, 22.468 degrees. Okay, so where can we use this angle? So in order for us to compute distance z based on the figure, okay, so when the liquid surface tilts, so it is equally distributed from the center. So if this side here, the depth of fluid changes, that change in elevation is just the same on the other side. So let's say this is distance y, this is also distance y, or the change in depth of the fluid. So let's compute distance y. So if this is the center, and we have a width of 1.7 meters, so this is 1.7 divided by 2. So half of 1.7 is 0.85 meters. So focusing on this right triangle here, we can compute y. Okay, focusing on this right triangle. So we use tangent function again to compute y. So y over 0.85, or 0.85 tangent theta is equals to y. So 0.85 tangent 22.468 equals to y, or simply y is equals to 0.85 tangent 22.468, that's 0.352 meters. Okay, we have y. From that, we can now compute the hydrostatic pressure at point A. So pressure at point A is just equals to gamma times H. So unit weight of water, 9.81 kilonewtons per cubic meter. So the total depth, we use simple Z. Let's replace this by H. Or simply, this total depth H here is just the sum of the initial depth, which is 0.9, and distance y. Okay, so that's 0.9 meters plus the distance y. Let me rewrite that again. 9.81 kilonewtons per cubic meter is multiplied by 0.9 plus 0.352 meters. So the pressure at point A is equals to 0.9 plus 0.352 12.282 kilo Newton per square meter. So the pressure at A is 12.282 kilo Pascal. That's the answer. Okay. For letter C, determine the force acting on the side with greatest depth. Okay. So again, when the vessel is in motion, so the side here with the greatest depth is this side here, the left side. Okay. So just to confirm class, based on the computed vertical distance, which is 0.9 added by 0.352, okay, that's 1.252. Okay, so it doesn't exceed the depth of the container, because if the total height is more than the depth of the container, the tendency is the water will spill on the container. So some of the water will be spilled out on this container, and we will have a new computation in in this problem. So in this example, there will be no water that will be spilled out. Okay. So going back to question letter C, let's determine the pressure on the side. Okay. So here we will just apply the hydrostatic force on plane surface, because force is required, okay, acting on the side. So what will be the hydrostatic force acting on the side that has a greater depth, just the greatest depth? Okay, so what will be this hydrostatic force right here? So since this is just a plane surface, a vertical face, so we only have one direction. Okay, force F, what will be that force F? So let's just write the total height, which is 1.252 meters. So from that, for letter C, we can compute the hydrostatic force, which is equals to gamma bar H times the area. So 9.81 kilonewtons per cubic meters multiplied by bar H. Bar H is what? So from this figure, so on the left side of this figure, we have a rectangle shape. Okay, the shape of the surface is rectangular. Okay, that's rectangular, which has a dimension of, the length of this is 1.7, and we have a depth of H, which is 1.252 meters. So the bar H is just at the center. Okay, from the center going to the liquid surface, so just take the half of 1.252. Okay, so divide this by 2, that's 0.626. Okay, so for bar H, that's 0.626 meters multiplied by the area. The area of the surface where the fluid is in contact with the container. Okay, so 1.252 by 1.7. So that's the area. 1.252 by 1.7 meters. That's your hydrostatic force. So let's compute that. 9.81 by 0.626 by 1.252 by 1.7. The answer is 13.071. 071 kilonewtons. So that's your hydrostatic force. Okay. We can also determine the hydrostatic force on the other side. Okay. You can also determine that. So again, 0.9, we subtract the value of y, we can determine this height, and applying the same solution where our area is smaller, so we can compute the hydrostatic force also. Okay, but since the required here is the one that has the greatest depth, the side that has the greatest depth, we only solve the left side hydrostatic force. Okay, so that's how you solve this problem. Next. So again, here's the question, class. What if when the body is in motion and there will be water that will be spilled on the container. So it will depend on the computed value of theta. So if your angle is so high, so supposed to be you have computed an angle that has a value that when you draw the new liquid surface, when it is in motion, the other side exceeds the depth of the container. So what will happen is water will be spilled on this side. So what will happen here is that that angle theta will be constant. Okay, it will not change on the process that the water will be spilled as it moves. So what will happen is, say this is your rim. Okay, so the liquid surface will follow the angle theta here, and it will end on the rim surface until it reaches this new surface right here. Okay, following the computed theta. So the excess water will be spilled out to attain this position of this new liquid surface as it is moving. Okay, so it is important that we determine the initial volume of the fluid, and if it is required there, we can determine the new volume based on the new position of the liquid surface. Okay, next problem. The tank shown in the figure is accelerated to the right. Width of the tank is 1.5 meters. We will determine the acceleration needed to cause the free surface to touch point A, and determine the pressure at point B. Determine the total force acting at the bottom of the tank. So this tank is a closed tank, so it means there will be no water that will be spilled out of this tank. So okay, let's say it is moving to the right. I have an acceleration here. It is required here that as it moves at a constant acceleration A, is the free water surface will touch point A. So it means if this is your initial position of the liquid surface, it will end up touching point A. Okay, so that's the value of theta. Okay, this is theta, this is theta. Okay, so this is a closed container. So what we will do here is that we will use geometry in solving theta. So since this is a closed container, this is a closed tank, so it means that there will be no water will be spilled. Therefore, the volume of air in this container before is just equal to the volume of air after the body is in motion. Okay, so the volume after. So let's compute first the volume of air before. Okay, so the volume of air before is 0.2 by width 2 meters and the length. Okay, that's 1.5 meter width. This is 1.5 meters. Okay, like this. If it is a rectangular prism, that has a width of 1.5 meters. So 1.5 meters. Volume of air after. So if the liquid surface touches point A, we form a right triangle. We form a right triangle. That's 1/2 base times height. So this will be your base. Say this is distance x multiplied by the total depth 0.2 plus 1. That's 1.2 meters multiplied by the width 1.5. Okay. So divide both sides. Actually, as 1.5 is cancelled out, we divide both sides by 1/2 and 1.2. Okay. So solution is x is equals to 0.2 by 2 by 1.5. Let's remove 1.5. That's 0.667 meters. Okay, so that's the distance x. From that, we can compute the angle theta. So using this right triangle form here, this one is a right triangle. We can solve theta by tangent function, which is equals to tan theta equals to opposite is 1.2. Okay, so that's 1.2 over x. So theta is equals to arctangent of 1.2 meters over x. Okay, let's substitute x, 0.667 meters. So theta is equals to arctangent of 1.2 over 0.667, 60.933 degrees. Okay, that's the angle. From that, we can compute the acceleration, okay, for us to attain this liquid surface at this angle. So using again the formula, tangent theta equals to A over G. So A over G, acceleration is equals to G tangent theta. So A equals to G tangent theta. So acceleration 9.81 meter per second square multiplied by tangent theta is 60.933 degrees. So the acceleration is 17.649 meter per second squared. That's the answer for letter A. Okay. For letter B, determine the pressure at point B. Okay. So let's have another figure for this. For letter B. So for closed vessels, so we have here a moving vessel. So in determining the pressure at point B, which is the side where we will have greater hydrostatic pressure, so compared to point A, which is the hydrostatic pressure there is 0 because there's no water above point A. So in the case of closed vessel, what will happen here is that the pressure head at point B, okay, which is supposed to be up to this point only, because when the water move, okay, this will be now your new position. Okay, this will now be your air. This is full of water. But in closed containers that is moving, the pressure head at point B is computed by when we extend this liquid surface to the point that it will intersect the side, when we extend also the side where we will find the pressure. Okay, so this is your side here at point B. Okay, if we will just extend the vertical line there, and we will extend this liquid surface following this angle theta. Okay, so let's say that's your line for this liquid surface. So that's your point of intersection. So if this is the point of intersection between these two lines, therefore the pressure head that we will use here in determining the pressure at point B is this height right here. Okay, this distance h. Okay, that's the total pressure head. So it means in a closed vessel, the pressure head at point P is more than, okay, more than as we compare to an open vessel. So when we compute that, the pressure at point P is just the product of unit weight of water multiplied by that distance h. So to compute h, we use tangent function theta equals to h over adjacent, which is 2 meters. So h is equals to 2 meters tangent theta. So 2 meters multiplied by tangent theta is computed already, which is 60.933. 60.933. Okay, so h is equals to 2 tangent 60.933, 3.598 meters. Okay, so from that we can solve the pressure at point P, 9.81 kilonewtons per cubic meter multiplied by h, which is 3.598 meters PB. Kilopascal. 35.296 kilopascal. Okay, so that's the answer for letter B. For letter C, determine the total force acting on the bottom of the tank. Okay, so what will be the total force acting on the bottom of the tank? Will be the total hydrostatic force right here.